Yesterday, we have gone through few important points of strain analysis by vector calculus. What we have done there, hmm, we have imagined how the deformation of it takes place in three-dimensional coordinate axis itself. What we have, the three-dimensional coordinate axis OX, OY, and OZ, as usual, and we have a irregular shaped body like this, which is given in a form line, and after the deformation, this body is supposed to take this this particular shape with sectional line itself. We are considering here the origin, x-axis, y-axis, and z-axis, and a point P, whose rectangular coordinates are known to us, is given as x, y, and z. Means the what do you mean by this x, y, z? If we drop a diagonal if drop a normal to all three axes, the distance from O to the point of intersection of the normal is given as the three uh, respective coordinates. Now we imagine that due to the action of some external forces, etc., the body concerned, which is given by this form lines, is deformed to take a shape of given by this sectional line itself, and this point P has changed its position to P dash, whose coordinates is also known to us even as x dash, y dash, and z dash. Now, here we have a displacement section, displacement vector P dash. You know, from the definition of vector analysis, the displacement, force, displacement, velocity, and accelerations are the vector quantities, which means they have a numerical value and they have a specific direction from which along which it is acting. It is the vector P dash is not exactly same as the vector P dash P because their orientation is exactly opposite. Line of action is exactly opposite. This is the theory of conception of vector analysis, which we are applying here. Now, this displacement of P to P dash, that is the displacement vector P dash, has is denoted generally by the term small u, which is the displacement vector P dash. The displacement vector that this now what happens here, uh, the displacement of this length, whatever small it may be, it has a component along x-axis and y-axis and z-axis itself. These components are given as ux, uy, and uz. And as per the definition of the vector, we can write u here is equal to I into ux plus j into uy plus k into uz. Now, this displacement undergone by any point is a function of its initial coordinates. We assume that now this displacement undergone by any point throughout this particular volume, which is being happened due to this action of some external forces, which is deforming to a different shape, and thus the original points looks a different position. And original components, we know the coordinates of the original component from our standard from our um, rectangular coordinate setup, and we assume this displacement is all displacement of particular points from the initial to final of any points throughout the length of the body is defined or available by the displacement vector u, and if provided the coordinates of initial coordinates and final coordinates are known to them. So what is this? Any point can be deformed. Due to the deformation of the whole body, any point acting over it is taken deformed and takes a new shape. And any such body which is supposed to be only belong to this particular body is known by its displacement vector. Means its displacement of that particular body, this all the bodies will displaced by the action of external forces. All the points on the inside the body is displaced by the wider action of the external forces, and the displacement is known to us always if provided we know the coordinates of the initial coordinates of the know the coordinates of the points. So displacement of points is given by the displacement vector, and the initial position and final position of all the points before and after of deformation is given by their coordinates itself. So what happens if we know the coordinates of the initial displacement vector and if r is the position vector of a point P, then we can say that r dash is the position vector of point P dash, then r dash will be equal to r plus u. Well, so we are getting two terms. One is displacement vector given by the displacement of a certain point P to P dash, and position vector which is given by the coordinates of the initial or final position of the particular point concerned. So two vectors are defined here, and we know if we know the initial position vector and the displacement vector, the final position vector can be easily calculated by this particular relation r dash is equal to u plus y. R dash is equal to r plus u itself. Just quickly go through a problem which we have discussed yesterday. Let a particular body, the displacement field or displacement vector is given by this equation u x square plus y into I 3 plus 3 plus z into I plus x square plus 2y into k. This is given. Now, what will be the decimal position of a point originally at deformed position of the point which was originally at 3, 1 and 2. So what we have the displacement vector here, and we have the position vector of the point initially. The displacement vector at, so what will be the displacement vector at E at U? There the position vector is given 3, 1 and minus 2. The displacement vector, if you put the value of x and y and z here and x square and 2y here, this will take 3 square plus 1, where x is equal to 3, I is equal to 1, y is equal to 1, 3 plus z is equal to minus 2, 3 plus z where z is equal to minus 2, and 3 square, 3 is the x to the power 2 plus 2 into y is equal to 1 here. So the displacement vector at u will become 10I plus j plus 211k. So by knowing the position vector and initially, we know the displacement vector there also. The initial position vector will be, as per the theory of vector analysis, this point coordinates is known, then it will be r 3I plus j minus 2k, where 3 comes from this origin of x1, x, 1 comes here, which is the coordinates of y, and minus 2 comes the coordinates of z. So initially, so we can safely find out the displacement vector and the position vector at the point P dash by adding this position vector with this displacement vector. Just 1 second. Okay. Next comes the point. Now let us come to today's lesson. Oh, here that problem is like this. It will take this particular form by adding this r and y, 39, 2j, and 9k. And if you want to know the coordinates of this point r dash, then it will be 13, 2, 13, comma 2, and 9, comma 9. Now let us go to the today's problem, today's cases discussion, which is much more interesting. Here we are again considering that rectangular coordinate axis x, y, and z, etc. We are deformed, get a body, irregular shaped body like this, and considering two particular points P and Q inside it. And what is the speciality of these 2 points is we are considering an area surrounding P, which is infinitesimally small or extremely small, but equal to almost equal to 0, but not equal to 0. And the P is a neighboring point of P which stays within this infinitesimally small area, which means the deformation from P to P dash Q to Q dash, it will be such that it is almost the deformation of P and deformation of Q will be more or less equal to that of uh, deformation P and Q is more or less equal to that of deformation of P dash and Q dash, but not equal. These have difference. Uh, this have infinitesimally small amount different elemental difference between them. This is created. This type of process is created to have the analytical calculation of knowing the deformation of point to point. Now, I just told you there is a P is a point with coordinates x, y, z, and we are considering an extremely small region surrounding the point P, and Q is another point within this region, but not outside the Q is infinitesimally close to P, and but not coincides with P itself. And we know the coordinates of P, which is equal to x, y, z, and as Q is extremely close to the P, we can safely say these coordinates are x plus delta x, y plus delta y, and z plus delta z, where P has the component along x and y axis as x, y, and z. So Q also have the component along x, y, and z axis with y is a size x plus delta x, y plus delta y, and z plus delta z. Now, due to the action of some mental forces, both the body, this body deformed, and as the body is deformed, both these points P and Q changes its position, and but both has displaced changes position. Both are displaced. So we have we should have the conception of position vector, initial and final position, and conception of displacement vector, which is as the point this is displaced from initial to final point itself. Now, let the displacement vector u at P. Let us consider first the point P. What is the displacement vector of the u at point P? Let us have the point ux, uy, and uz is the displacement vector. Means if point P is displaced to P dash, the component of this displacement P dash along x and y and z axis is given by ux, uy, and uz, and that is the displacement vector u. The coordinates of P and P dash are thus P x, y, z, and P dash as uh, it is displaced by the amount ux, uy, and uz. P dash coordinates of P dash will be x plus ux, y plus uz, and z plus uz itself. Now let us come to the point Q. Q has the coordinate we have just mentioned, that x plus delta x, y plus delta y, and z plus delta x. And the body undergoes deformation, points P and Q moves to P dash and Q dash. Means P moves to P dash, Q moves to Q dash. So the displacement vector u at point P, just I am saying you, sure. Just 1 second. Thus, we have the components. The displacement vector u at p have the components ux, uy, uz. Means we have just tell you again. I'm telling you again. Means p is displaced from p to p dash. Thus, the distance p dash have the components along x and y and z axis is equal to ux, uy, and uz itself. Thus, the coordinates of p becomes x, y, and z. Coordinates of p dash becomes x plus ux, y plus uz, and z plus uz itself, as the point p is changed by this amount of coordinates ux, uy, and z. So we are just adding the value to the initial value of the coordinates. Q we have decided as Q is infinitesimally close to P, their value, the coordinates will not be equal to P, but slightly different than P. With x plus delta x, y plus delta y, z plus delta z itself. Just quickly recapitulating a few points about the vector analysis, which will be helpful. Any vector in 3 dimensions can be represented with initial point, say 0, 0, 0, and the final point a1, a2, a3, such as our cases p initial point with coordinates x, y, z, and final point with coordinate x dash, y dash, z dash. So the vectors a1 into I, a2 into j, a3 into j is called the component vectors. Means the distance from a to initial point to a dash, final point is a1, a2, a3 in three respective directions, and a1i, a3k, a3k are defined as component vectors of a. Thus, in the x, y, z direction, the scalars a1, a2, a3 are called components of a in x, y direction. Sum of them gives the vectors of a. So we may write that a1i, a2j, a3k. The magnitude of a is the square root of a1 square plus a2 square plus a3 square. If a point xyz in space, the vector from origin O to the point P is called position vector or radius vector. Which we have discussed the position vector of P, means distance of vector r from the position origin O to the point P is position vector, means its coordinate, which is the component of this vector in x, y, and z direction, is the position given as the position vector. Or you can say the radius vector if we use the vector r itself directly. So this r is written as xi, yi, zi, yi, zk, which is xi, yj plus zk, which is given as its magnitude is given as x square plus y square plus z square. This portion is we are applicable to our present work itself. Now, next comes, just 1 second. Now, next comes the displacement components of Q will differ slightly from those at P, since Q is always away by an amount del x, del y, and del z. Now, what is they mean by that? Q is displaced to Q dash, but initially Q is not equal to P. That because its position is slightly away from P by delta x, delta y, and delta z. It is the elemental distance or differential distance, but it is not equal to 0. So the displacement of Q dash will be ux plus delta ux, delta uy plus delta uy, and uz plus delta uz. Ux is the component of displacement as of x, y, and z, ux, uy, and uz. But as the component of the coordinates of Q is defined is changed by the coordinates of P by amount delta x delta z, their displacement vector also change, and the change will be added like this: ux plus delta x, uy plus delta z, uz plus delta z itself. But how will you know the value of delta uz or delta ui or delta uj? This is given by this equation. If q very close to u, then just just order to have just first order application we can make. Delta ux will be delta ux by delta x into dux by dy, uh, dux by dx by delta x, dux by dy delta y, and duz by dz delta z, which means rate of change of ux by the distance x along x-axis multiplied by the distance which is already sustained. Rate of change multiplied by the distance, and rate of change of ux along along y-axis multiplied by the actual change which take place, and rate of change of dz divided by yz along z-axis multiplied by the actual difference in delta z, del z. So if you calculate this thing and add them together, you'll get the value of ux. And from the first and the right hand side is the rate of increase of ux. So rate of increase of ux, rate of increase of position vector, or rate of decrease of the component of the x component pp along x-axis is multiplied by the distance traversed, which is multiplied by the original original change of the distance, or original change in the coordinates, which is delta x itself. The second term is the rate of increase of ux in terms in y direction, multiplied by the actual distance traversed by y direction, that is delta y. Similarly, z third term, the rate of change of increase of ux along z direction multiplied by the distance traversed by z direction, that is delta z. So this is the way we have find out the change in the position vector delta ux. For the similar way, we will calculate the change of uy and change of uz along y-axis and z-axis, duy dx delta x, duy by dy delta y, and so in the delta z. Same is the case with delta z, duz and delta x, dx delta x, and dy delta x. So what we finding here is to be y, not x. Now, what is very clear in this function, as q is away by x by delta x, their position vector is also changed by to a certain amount. They are not, position vector of q is not equal to ux, ui, or uj, but they will differ to a certain extent. So how do you know? We differentiate the ux, the original position vector, by x dx, and you multiply it by the change in position. Actual change in position means x is changed to x plus dx, that the change in position is dx. Similarly, change of ux in terms of y should be multiplied by the change of the coordinates along y direction. Take the uz, or the position vector along uz, direction cosine along uz, divided by dz multiplied by the change in z coordinates along z axis itself. Same is the case delta y, delta uy, delta uz, and delta ux. Same, always we are having ux, uy, and uz, ux, ui, and uz, and d, and all are divided by dx, dy, dz, dx, dy, and dv, and multiplied by the change in the coordinates delta x, delta y, delta z, delta x, delta y, delta z. So these equations are more or less similar, and we can form a matrix with it like this. So transfer these coordinates to q dash. What happens? Q dash becomes delta x, delta um, x plus delta x. Q dash will be x plus delta x plus ux plus delta ux, y plus dy delta x plus uy plus delta uy, and delta z plus delta z plus uz plus delta x itself, delta u delta z itself. Before the deformation, the segment PQ has component delta x and delta y along the three direction, delta x, delta y, delta z. And after the deformation, it has component delta x plus delta ux, delta y plus delta uy, and delta z plus delta uz along the three axes. The terms like delta ux, delta x, they are delta ux by dx, delta uy by dy, and delta uz by delta ux by dy and delta ux by dz are important for the analysis. So these are given. They are the gradients of the displacement components at p and xyz direction. One can represent in the form of matrix called the displacement radial matrix also. This displacement gradient matrix also. Thus, delta u by delta x y, we put all this coefficient of delta y, delta z, delta y, delta z, delta z along these three particular direction along the matrix right here. This is for delta ux, this is for uy, this is for uz. So as a whole, it can be written like this: delta u to the power I from stands for x, y, and z. It will alternate in a regular fashion. Delta xi, it stands for j stand for also 1, 2, 3, etc. Now, let us go through, understand through an experiment, through a practical solution. Delta uj by delta xi. Just 1 second. Okay, let us have the following displacement field is imparted or imposed on the body itself. U xy u is equal to xyi plus 3x square z into j plus 4k whole multiplied by 10 to the power minus 2 or 1 by 100. Consider a point P and a neighboring point Q where PQ has the following direction cosines: ux 0.02, ey in nx is equal to 0.02, ny 0.08, nz 0.555. P has the coordinates. P has the coordinates 2, 1, 3. If PQ means distance from P to Q is delta S, written as delta S, find the component of P dash Q dash under the deformation. So displacement field or displacement vector is given here, where you have to put the, if you want to know the position vector of each point, you have to put the coordinates of respective coordinates itself. Next, another thing is given here: nx, ny, z direction cosines of PQ. It is but not P dash. It is the direction cosine of PQ, means the angle subtended by the cosine of the angle subtended by this length PQ along x-axis, y-axis, z-axis, and the point P initial point is given, and point PQ is rated as delta S. So what we are supposed to do? Now, before the deformation, the components of PQ are given as delta x, delta y, and delta x, delta y, and delta z. How nx reaction cosine is given of PQ. So if we multiply it by the distance delta x with this direction cosine, we'll get the value of delta x, which is the difference in coordinate between P and Q. The distance PQ is given, its direction cosine is given, and its length is given by delta x. If we multiply direction cosine, means which is the cos of that cos of the angle subtended by that particular straight line along x-axis, y-axis, and z-axis, and if we multiply it with the length, we'll get the x coordinates of increase in x coordinates delta x, increase in y coordinate delta y, and increase in z coordinate delta z. So put the value of nx, which is known to us, which is 0.2 delta s, put the value of y, which is known to us, which is 0.8 delta s, and put the value of z, we known to us, it is 0.555 delta s itself. From then what I got from equation 456, that is the equation of last page, the values of delta x, delta y, and delta z. Now we have this vector, we have term 10 to the power minus 2, we just replace it for our own, it is equal to p. So if we put the value of x, y, and z, if they put the value of ex, we have to put the value pxy, where ux is equal to pxy, which is given in this equation. P is this portion, p multiplied by xy, then p multiplied by y squared z, and p multiplied by 4. This is ux, uy, and uz. That is the uh, distance point along the axis px. Along the axis pp, that is the distance vector, position vector, px, py, and pz. Ux, uy, and uz given by this particular formula itself. Now, if we want to know the rate of change of ux by dx and uy by dx, dz by dx, if we have to differentiate this ux, uy, and uz by x and y and z, a result for the ux is equal to py, for uy is equal to 6pxy, and uz is equal to 0 because both are constant. Similarly, ux divided by uy, pxy, uz, yz by dy, 3p square, and delta z by dy is equal to 0 itself. That goes up to 6. Share 6. Similarly, if we integrate by z, the dux will be 0, uy is equal to 3x square, and uz again 0. Now at the point 3, which is given, initial point P, 2, 3, 1, therefore the ux will be delta ux will be delta uz plus delta x uz into P. So we put, it is coming from the initial equation P. Because as we know, the point P234 is equal to delta ux y into dx, delta x dx, x delta x P, that is given by delta x plus 2 delta y into P, and delta y is equal to 6 delta x into delta x plus 3x squared into delta y into P. As a whole, 36 delta x and 12 dz and P, and delta x 2 delta y into P. So how this happen? The value of delta z and delta y, how can you calculate? First of all, we put the we are changing the asking go for the change in delta x, delta y, and delta z, and we put ux, uy, and uz from the difference dispersion vector itself, and delta ux is given from the formula 456. Delta ux is given as ux rate of change of ux by uy, delta ux by delta x, which is given here equal to py, which is equal to py, and p is put outside the bracket, and y is there multiplied by delta x, and uh, delta uj by uy we have just calculated here, which is equal to 3x square is equal to 3pxy. So we get we put xy p outside it, and x 6px square dy by dx. We put p also outside it, and put the value of x here, and z is always 0. So that is equal to delta x into delta y is taken out, xy, delta x plus 2 delta y into p, and delta y 6 delta x z into delta x itself. Similarly, delta z, uh, delta u, we have to put the value of delta u, ux by delta ux by dx into delta z like this. To this equation, take this particular shape, and uz, as all of them are equal to 0, the uz, delta uz equal to 0. So substituting for delta x, delta y, and delta z, the component of delta is p by p square, delta x by delta x by delta x is given as both the values are placed here, and we will take the value of 36 delta y, delta 1 to 0.72. That's 0.8, 0.6 delta s itself. Because we know the value of delta x in terms of delta s, so we have put the value of delta s and take by simplification take this particular form. That is equal to addition to 0.9939. Similarly, delta z can be calculated accordingly, and now the new vector become the new vector will become p dash q dash is equal to 2.28, putting the respective values of delta x, delta y, which is our distance of vector. So this will take 0.218 I, 0.939 j, and 0.555 k. This is thus we have got the final vector new j. So everywhere we are using this equation, these three equations of change, rate of change of delta x, delta ux, delta uy, and uz, then adding together, we get the final value of delta x itself. We are at the end of our search, so let us stop it, and I'll go for the next stage in Tuesday.